Dear friends, fellow attendees, and esteemed guests of the Pan IIT World of Technology 2021 Summit. The cutting edge theme covers the latest and most exciting advancements in computers, space, transportation, robotics, and manufacturing, which advances human limits. A deep dive into the new possibilities and the groundbreaking innovations in these technological frontiers will help us uncover everything from the functioning of particles to the universe, from protecting the environment to augmented manufacturing systems. To inaugurate this wonderful theme, consisting of some very exciting panel discussions, let me welcome our keynote speaker for the cutting edge technology theme, Shri S. Somanath, who is currently serving as the director of Vikram Sarabhai Space Center since January 2018. He has also served as the director of Liquid Propulsion Systems Center, associate director projects of Vikram Sarabhai Space Center, and also the project director of GSLV Mark III launch vehicle. Shri Somanath is an expert in the area of systems engineering of launch vehicles. He has made contributions in PSLV and GSLV Mark III in their overall architecture, propulsion systems, structural dynamics, separation systems, vehicle integration, and integration procedures development. He received the Merit Award, Performance Excellence Award, Outstanding Achievement Award from ISRO, and the Team Excellence Award for GSLV Mark III development. Shri Somanath is also the recipient of the Space Gold Medal from Astronautical Society of India and the National Aeronautics Prize by the Aeronautical Society of India for the year 2018. He was awarded Doctor of Philosophy honoris causa by Satyabhama Institute of Science and Technology, Chennai. Shri Somanath is a fellow of the Indian National Academy of Engineering, fellow of Aeronautical Society of India, Astronautical Society of India, and a member of the International Academy of Astronautics. He is the Vice President of International Astronautical Federation in charge of the technical activities. Please join me in welcoming Shri S. Somanath to the virtual stage. Over to you.
Thank you. Good morning, all of you. Thank you so much for the introduction. I'm really honored today to be part of this Pan IIT session and also to deliver the keynote. Before I go further, let me upload a PowerPoint. I hope that it will come well. Let me try now. Hope the PowerPoint is visible. Okay, thank you. Thank you for the opportunity once again. For the opportunity to present to the Pan IIT and the World Technology Summit in the cutting edge stream and talk about space technology. See, if you look at the Indian space program in a nutshell, in a summary, you will really realize that in the last 50 years or so, the significant accomplishment has been achieved in this domain. Some of them being very, very, very important. One of them being to have our own capability to build our own spacecraft and have our own launch systems to launch it from our own soil. And this is not a mean achievement. See, if you really look at the number of launches that has been accomplished, we have achieved almost 81 launches of all launch vehicles. We have 3 operational launch vehicles today. And the number of spacecrafts that you have put them into the orbit includes communication, remote sensing, navigation satellites, and also science missions. And currently, almost 50 satellites are serving this country in various domains. We also engaged with the global partners, global space agencies, also commercially engaged with our launch vehicles, put 342 satellites in orbit, including mini, micro, nano, and big satellites from almost 34 different countries. You engaged with the many nations and agencies for scientific missions where their payloads were hosted, joint research was conducted, joint MOUs were signed. There were also technology developments in addition to the rockets and satellites and applications, where many new technologies which is actually seeding into the future, like the crew recovery experiment, crew escape system demonstration, reusable launch vehicle experiment, air breathing engine development, all of them leading to a future prospects of exploration. So this is what we stand today. And me being part of this journey in the last 50 years, I have been there with the Indian Space Research Organization for last 35 years. And being part of some of these great achievements really makes me very proud and humble. And to talk to you on the cutting edge in the space domain, I hope that makes me eligible really today to speak about it. But at the same time, if you look globally, what is happening, all of you know what has been accomplished world over in all the spacefaring nations. Today, in India, we have bridged the gap between those great spacefaring nations in a significant manner in terms of launch capabilities, satellites, and applications. But what is happening today in the global space scenario is really astonishing. Yesterday, we heard about a launch of civilians to space in one of the launch vehicle. There has been attempts by human beings to go and cross the Kármán line, stay in orbit and come back, or even outer space and then come back. There is a development going on in launch vehicle, the conventional launch vehicle called the expendable launch vehicles, returning, reusing them multiple times. And also looking at explorations further to go to Moon, Mars, creating the Artemis program. And new human-rated crafts are being developed at many places. But also at the same time, I am also watching and seeing many startups coming up in the space enterprise, not only in India, but across the globe in large numbers, building small launch vehicles, building spacecrafts. And also that yet another side, people talk about colonizing and going to Mars and in large numbers, making use of the launch vehicle technology as a platform by which you can really engage in economic travel across continents. This is another type of inspiration that is happening in space sector. We also look at very cutting edge development in communication and remote sensing through an array or a cluster of large number of satellites deployed across low Earth orbits. New links, Starlinks, OneWeb, and other clusters are coming up, constellations are coming up in low Earth orbit, which will really transform the way we have been using spacecrafts for communication and imaging and providing connectivity in such a way that you can never imagine that you are actually using terrestrial or satellite systems in a seamless manner. And these are the type of technological revolution that has been happening in the last few years. Even amidst the pandemic, you can see the type of activities really upsurge. Now look at the Indian space transportation system. Me coming from specifically from launch vehicle design area, I would like to focus on the cutting edge technology and development in that domain significantly, but also I will try to look at some of the other domains like spacecrafts and applications. Now, if you look at the Indian space program in terms of transportation system, I can put it into 3-4 different tracks in which the operational launch vehicle like PSLV, GSLV, and GSLV Mark III are transitioning now from and operating on a availability domain to a demand-driven framework in which the launch vehicle will move over from ISRO to industry, and they will be providing the type of manufacturing, assembly, integration, and services to the customers. And slowly it will graduate into a fully industry-driven launch vehicle model in which the commercialization will be based on demand profile. So this is for the operational systems. And new satellite launch vehicle is entering now, the small satellite launch vehicle, looking at the emerging market. We also have technology developments basically for enhancing the capability through various propulsive modules development, semi-cryogenic stages, and bigger launch vehicles to look at the future transportation needs. Yet another domain is leading to the technology growth, like the reusability for conventional vehicles, the winged vehicle that has to come back, air breathing integration in the launch vehicle, etc. This is yet another plan of action. While doing on these bigger projects, we also want to continue working on new initiatives which will really keep us engaged in the emerging scenario, changing scenario, which includes new propulsion modules, looking at greener propulsion, like LOX methane, looking at high thrust engines, developing new materials that will feed up into the new programs like miniaturized avionics, bringing in robotics, automation, quantum technologies, artificial intelligence into the domain of space technology. All these are yet another research and development activities that is currently going on across all centers. So this is the overall framework on which the space program currently operates. So all this really leads to a set of launch vehicles, missions, possibilities like the heavy lift launch vehicles, maybe a super heavy launch vehicle, and reusable launch vehicles or orbital vehicle, which will serve in orbit and then come back. Basically, the type of space shuttle type of concepts in which it will be fully autonomous, not man-rated, which will be able to do certain type of research activities or experiments or deploying certain missions on board the orbit and then come back and land, and then we recover them and then reuse them. So these type of missions are still very important and strategic in nature. While we work on this, we also look at spacecrafts in terms of high throughput satellites. One side we talk about very, very small satellites, but other side we talk about huge satellites, which can be still made smaller by injecting electric propulsion, high throughput data rate systems and antenna, which serves specific communication requirements, and also scientific and deep space missions as well. One of the interesting things we work is autonomous Scramjet flight testing. It is basically an air-breathing engine, which is basically working on kerosene as a fuel, and air will be taken in and compressed in such a way that in hypersonic condition, it will be combusted and then generating thrust to accelerate the vehicle and produce tremendously high speeds. This technology is very strategic in nature that today it may not immediately feed into launch vehicle program, but it has very other connotations. But the most important thing we look at in this technology is to understand various domains, like, for example, computational domain in fluid dynamics, where we look at scramjet, combustion, compression, chemical reacting flows, and predicting the type of combustion and pressure variation that will occur in the expanding nozzles. And also look at high temperature materials, which will withstand 2000 plus degree temperatures. And design of the vehicle and integrated manner, a fuel, frame, engine, all integrated in a single frame, and designing a control system which will take this vehicle all along in through a thrust and aerodynamic control surfaces and conduct long duration mission through air. Now, all this really will feed the technologies into the future launch vehicle programs. Yet another interesting technology we are working is, of course, technically, we know that vertical takeoff and landing has been accomplished elsewhere. But when you talk about India and ISRO, this is another domain we need to enter into and then perfect it. And a few of the technologies coming here are the propulsion itself, where we work on retro propulsion with engines having deep throttling capability. We have to have landing systems and control system while retro propulsion is going on, and then smooth landing has to be accomplished through landing legs, fin controls. We also need to have navigation guidance with very, very good accuracy and aided navigation, especially laser-based and vision-based navigation systems, which will lead to very precise landing of these crafts. World over, we realized that the move from conventional engines called hypergolic engines to eco-friendly propellants, such as kerosene and methane, is very much going on. And most of the new developments in launch vehicles are more centered on such technologies, because methane is a fuel for the future. And in line with that, we are working on kerosene-based engines called SemiCryogenic Engines, and quite a bit of activities have progressed, and we are now reaching towards an integrated engine test. Another interesting thing I want to share with you is work on LOX methane engine in our facilities, where we have tested one of the engines for the initial ignition trials as a technology demonstration. And slowly we will be going towards the real engine development in LOX methane combination. Look at more greener and more environment-friendly propulsion is one of the important thrusts. For example, in spacecrafts, we continue to use very carcinogenic fuels, chemical fuels, even today in most of the spacecrafts other than electric propulsion. And it is necessary that we move from hydrogen-based satellite thrusters to hydrogen peroxide-based or ADN-based thrusters, which are more environmentally friendly, catalytic-based thrusters, which will generate no contamination. And the production and testing of this is one side of activity, slowly getting into the spacecraft systems. And in the launch vehicle side, yet another area is called the hybrid propulsion, where we use fuels in solid form and it will be regulated and controlled in combustion by the induction of liquid oxygen as the oxidizer. And with this, we can generate a throttleable solid boosters, may be useful for controlled thrust and descent and landing and vertical takeoff in a very specific requirements. And we have tested one of these hybrid rockets very successfully in recent times using solid fuel and liquid oxygen as the oxidizer. Yet another critical technology, very cutting edge technology is electric propulsion. Electric propulsion, as you know, that the generated energy from solar panels stored on board used to generate thrust in a satellite for orbit racing or attitude control processes. So here, the advantages in terms of improved specifications, improved efficiency of the chemical propulsion. Here, and by simply introducing such thrusters, we will be able to get payload capability significantly higher. Basically, you can build a 5.5 ton spacecraft in 3.5 ton, which means that you can use the remaining 1.5 ton into conventional communication payloads, any other payloads that will really enable the capability of the satellite to be better utilized. So this is one side of the development. We were successful in testing some of these thrusters on board the spacecraft, and we have a plan to inject these thrusters in the future launch vehicles. We may be able to develop thrusters as much powerful as 1 Newton, though you look at a very small number, but this thruster value is very, very significant and important for a satellite of even the 5 to 6 ton class. We are also working on RF-powered plasma engine, where a 10 kilowatt RF-powered plasma-driven engine could be developed using the available technologies. In the electric propulsion thruster area, there are yet another type of things where we use krypton-based low-power electric thrusters required for very small satellites, and also magnetically shielded zero-erosion stationary plasma thrusters for long-duration missions. The criticalities in this, or the very important technologies, are materials here, especially which has to withstand very high plasma conditions without erosion and long life and not to cause any damage when they work for 20,000 or 50,000 hours with non-stop. And these are the type of material demand. Even magnetics is a very important topic here. And power conversion efficiency, the DC power which is available to be converted to high frequency, high voltage power without loss of efficiency, is another important technology which is feeding into electric propulsion. Nuclear propulsion area is another where there were many nuclear engines earlier, but to use nuclear energy on board spacecrafts and launch vehicles is not really welcome. But using the radioactive isotopes, it is possible to generate heat as well as power on board, which will really enable use of such systems for spacecrafts, especially for long duration and interplanetary missions. And here we are currently doing some of the developments in collaboration with the other agencies which are involved in this domain. Probably in this cutting edge track, you will be discussing additive manufacturing as one of the very core area. As all of us know that this is one transformative technology that is changing everywhere. With regard to space, inducting additively manufactured product really enable very big optimization, especially in topology optimization, and also generating designs which are conformal in nature, like cooling passages to be inducted, even multiple materials that can be integrated. So here the whole goal of the development is in understanding the additive manufacturing processes in the metallurgical sense, in creating parts which will be able to survive the harsh demands of a space program, like high reliability, minimal defects, distortion and residual stress minimization, understanding the process of printing in various techniques, which includes a powder bed fusion or electron beam melting or even laser. To understand the whole mechanics of the printing is one of the domain that we are trying to work out, and then create a center of excellence in the area. We started injecting this additive manufacturing products into our launch vehicles and satellites in a very calculated and calibrated manner already. Another domain is energy storage. In space, once you go out of Earth, the only energy available are either chemical energy in the form of fuels or solar energy in the form of sunlight, which is converted to electric power and stored on board in batteries. And this has to be used for various activities. Lithium batteries is one of the important technology which you have developed in ISRO and even commercialized. But we are continuing to work on this to make it more economical, basically using the new chemistries in the lithium metal, silicon-based, or even sodium-based technologies. and finally leading to an all-solid lithium-ion batteries, which can be left without any great danger which is associated with typical lithium-ion batteries. And we also work on fuel cells, which is very, very important for long duration space program. We work on supercapacitor, where supercapacitor, which gives you high discharge capability and low current requirements simultaneously. This type of technologies we are working in the space program. And all of you know that one of the important cutting edge work is in material science. So I don't want to dwell on metallic materials, etc. But you look at the functional materials, dielectrics, magnetics, and optic materials. And here there is a big research work going on, especially in the dielectrics in ceramics for RF applications. And this is very important. And similarly, looking at the ultra low temperature, so cold ceramics, which goes into the electronics industry, magnetic material that goes into making new electric propulsion thrusters, new valves and motors and pumps and regulators. And also it feeds into the electronics parts and manufacturing. Optical systems with especially looking at the low thermal expansion glasses, non-linear optical materials, magnet-optical material development is really going to feed into scientific instruments development for the space program. Carbon composite is a very, very important area. It's not only carbon, but all other forms of composites. The thrust today is into manufacturing of carbon or composite-based products for various applications, because it gives you such a flexibility in terms of engineering a low weight, high stiffness, high functionality materials such as spacecraft systems, antennas, solar panels, propellant tanks, satellite structures, launch vehicle structures, payload fairings, and various manufacturing processes have come into composites. But the criticality today is in looking at high strength, high modulus fibers that can really transform this domain. And we really have a shortage of such sources in this country, and we need to get into this area. With regard to manufacturing, we are looking at more non-conventional way of manufacturing, which includes extrusions, 3D printing in composite structures. In the electronics area, there has been a lot of achievements in Indian space program, looking at Indian industrial manufacturing many of the passive devices, some active devices, and also even making a processor called Vikram in both 16-bit and 32-bit domain. And these processors now power most of the electronics and computers on board our launch vehicle program. But we need to work much better in this area, especially going towards the high power devices, IGBT drives, RF devices, FPGAs, memories, and mixed signal ASICs. And finally, if you want to really make an impact in this domain, we need to have indigenous capability of world-class foundries coming out of this country and setting up manufacturing plants, which will meet not only space program, but also the commercial electronics industries. Artificial intelligence and machine learning has already made inroads into our lives in such a big manner that space is no exception. We have already taken it as a very important domain to looking at issues like intelligent vehicle health monitoring, where we can introduce this AI capabilities tools into our avionics, propulsion structures, thermal protection, power and actuations, evaluation during flight, and then make certain assessments and reconfigure them. We also want to look at AI and ML to look at our prediction capabilities so that our mission can be managed en route by looking at optimization to extract maximum energy out of the rocket system. We also can use AI for fault diagnosis and prognosis activities. So these are some of the domains of AI which you are already exploring and trying to introduce in the coming missions. Space robotics has been very much in place. We have already used some of these capabilities in our Chandrayaan mission, where we designed the rovers, etc. But one of the important projects which are coming is to introduce tethered robots in one of our space for orbital platform, use capture systems to tethered satellites and bring it back to the stage. And really, this type of capabilities help us in issues like debris mitigation, refueling of satellites, and also to do certain specific scientific missions. There is also a robot being designed, the Vyomitra, which will be put in our Gaganyaan program even before the human being flies. Quantum technologies also are into space programs. See, quantum technologies, as you realize, that is one of the transformative technologies where we are looking at the quantum entanglement studies through a payload, and we would like to experiment it using our missions. We also have done certain successful experiments in short distance quantum communication. And one of the objectives is to study the radiation impact of spectral power distribution performance while this is on board, and also to evaluation of quantum receivers and time tagging, and also the end-to-end quantum key distribution technology as an in-orbit demonstration is yet another work we are currently working across the centers of ISRO. While we work on satellites and launch vehicles, one of the costliest system is the navigation system, inertial navigation system, which is essential for the success of the mission, and is very costly today. So we have been trying to work out a low-cost option for commercial exploitation through MEMS-based sensors, which are assisted using the NAVIC system, basically the positioning system support which is provided by the NAVIC, and integrating them, how we can really build a system which will give position, velocity, and attitude aiding for our launch vehicle program. We are successful in developing such a system, and this is possible in case of a thrusting time or a non-thrusting time, and non-thrusting time which will be supported by magnetometer support. So such packages are which at a low cost has also been realized and going to be integrated for forthcoming missions. Drones are now, it is tech enabled now. Drones can do communication, drones can do remote sensing, and they can be controlled using spacecraft, and all of them will be AI driven. So where are the type of applications? It will go into agriculture, it will go into transportation, security, delivery, medical, or even war application. Type of the drones may differ, and where there are different types of drones, which for short duration and very long duration stay in atmosphere. And with the spacecraft systems coming up, there is a need for transportation fleet control of drones, and there is where the space comes in. So one of the capability we are trying to build today is for a division maze navigation and landing of drones, and how to enable such simulation capability in our organization. So we have worked on a vision-based navigation simulation setup for drones, which will enable us to design these systems for future landing in other planets, or even vertical landing of launch vehicles using such simulation system on board. So one interesting project that has come up with using drones is to capture the spent stage of a rocket and bring back. So we looked at how a formation flying of drones or a drone net technology really can be demonstrated today using a formation flying of 4 drones carrying a net, can recover a stage which is being decelerated or brought to a velocity. Here we look at various communication technologies between the one which is falling and the drones, and in such a way that the net will have 0 impact loads by adjusting the velocities. And then once captured, it will be brought back to the land and then be used. So this technology demonstration will happen, which will really revolutionize some of the reusability concepts that we are having today. We also work on human spaceflight technology enhancement. Even after the first human mission is accomplished, we would like to sustain this program in a long duration domain to look at how to continue this, and what are the technologies which are required to keep this going. This is one area of domain of activity which I am not going to go through, but what is more interesting to me is to look at how the present system can be really improved. We see a human spaceflight mission is really very critical and very tricky in terms of safety, security. So we have so many different technologies being developed. I am not going into the finer aspect of each of them, which includes the reusability of some of the items, even controlling a solid propulsion system using vector control. So, and also look at inflatable habitats, environmental control and life support systems with much more compact and efficient systems. So these are some of the development activities which are required in human spaceflight. I also want to highlight some of the disruptive technologies which are currently under discussion. One of the interesting thing is a self-heating rocket, or called autophage engine, where the stage itself consumes with the propulsion. So the matter which is there in the rocket will become the fuel, and the body itself vaporizes and then produces thrust. So this is one type of rocket and concept we are working on. We are also working on self-healing and biomimetic materials, where there is a damage occurring and there is an intrinsic repair system available in the material that will solve it. Or there could be a trigger which will cause an extrinsic repair. For example, in a carbon fiber composite, there are certain microcapsules filled with the resins and catalysts react and then then heal those damages. Yeah, there are materials which are self-destructing, where you don't want to see them, the post functionality, like high nitrogen compounders, where the chains will be broken and it will depolymerize to become vanishing with the reactivity. Another area is additive manufacturing in zero gravity or microgravity environment, and we are planning to look at how to design a payload which can demonstrate such a microgravity printing activity, because gravity do affect additive manufacturing processes. See, finally, let me tell you that the goal of space program is application. So even after you do all these technologies, propulsion, structures, improvements in technologies, miniaturization, finally it has to do delivery of data to people. So data products delivery from space, which is an instant delivery, is an important goal. So for that, you look at the connectivity that we have today in terms of your devices streaming videos, where you will integrate the satellites, drones, or terrestrial tools seamlessly. So this is the technology which is required. And communication has to be directly to the individual, connected always to the web. And this has to happen through the satellite system. Timing and positioning services through various systems are required. It is also to serve for drones and the transportation system in general. We also have to integrate the satellite and space systems to the administrative network, as well as to the day-to-day life of a person or a human being. Then really the space will make a big impact in terms of technology. You also realize at the same time, we'll talk about the societal services. We realize the space technology is really a strategic technology for the nation, and it is something to be preserved because it affects your security. It is important for your surveillance and as a force to be reckoned with. So with this, let me look at I try to cover some of the cutting edge activities which are happening beyond the regular work which we do in building rockets and satellites. I think this really will be very beneficial for those who listen to this program, and really thanking each one of you for giving this opportunity to deliver this keynote talk on the cutting edge track. Thank you so much. Thank you.